Your thermochem unit test is coming up in Chemistry 30. Here's a quick little study guide you can go through. So the first one is just a slide of what you need to know. I'm not sure what's happening with the formatting right here, but the first formula you learned was Q equals MC delta T. We want to know to use this when you're heating or cooling a substance, so there's no chemical reaction. The next one, once we've learned enthalpy, is to see how enthalpy can change. So that formula is NH equals delta H. And then when you're writing this formula out, this part here comes from the reaction. So you want the enthalpy of the reaction, and it is a molar enthalpy. So divide by the amount of moles it's asking for. So because it's the enthalpy of the reaction, it is a delta H value within the reaction, but that's not what we're looking for in terms of delta H here. So just make sure you're putting it in the right place. This delta H is what's being released or absorbed to the environment. The next part is NH equals negative MC delta T. That is for calorimetry. So when you're looking at that formula, that NH equals negative MC delta T, just remembering that this side is all about the water and this part is about the reaction. And the other part, just to mention here, because of this C value and the units, joules per gram degrees Celsius, when you are solving for enthalpy, so the H value, your final value will be in joules. Oftentimes they'll want it in kilojoules, so you'll just make one extra conversion. I wrote in here as well to, when you're doing calorimetry, make sure you remember those three assumptions. So like no heat is exchanged, we have a closed system, and all aqueous substances will have the specific heat capacity of water. Now, the other type of calorimetry you can see is bomb calorimetry, and that's when not only are you looking at the first part, just like we did over here, so the reaction in water, but you have to add on the container. So you'll get a value for the specific heat capacity of the container, the mass of the container, and the temperature change of the container. Now, this is my really quick way of writing Hess's Law Short's formula, and that is getting the sum of the products, subtract the sum of the reactants, and we're using all those values from page 4 or 5. Now, in terms of concepts, the first concept you've learned is that the original source of all energy comes from the sun. You also want to remember that you have the sun to start, and then you have photosynthesis. So let's just draw a little flower here. That's a flower. Then you have bacterial decay, so things die, and that's how you get fossil fuels. And once you have those fossil fuels, then we can have reactions like combustion. That's our main one, and then just different types of combustion, whether it is within a vehicle or within a factory or whatever type of reaction there. That's our flow. We went on to learn endo versus exo. So you want to remember that if you have your endothermic reaction, that when you write it out, your delta H will be on the reactant side. If you have an exothermic reaction, then your delta H value will be on the product side. If your delta H value is written on the side and it's endothermic, it's positive. If it is exothermic, it's negative. So then the two ways you can see it. We have those formulas we just talked about. We talked about the three assumptions. We've talked about bomb calorimetry. Then there's Hess's Law long, and this is when you have the series of equations that you're using to get to your target equation. You also have Hess's Law short, how we talked about that. You also want to know your potential energy diagrams. So again, if it's endothermic, just adding on potential energy will look like this, where your reactants have less energy than the products. If it's exothermic, you see that drop where your reactants have more energy than your products. Your delta H value is always between the products and the reactants. Doesn't matter which one we're looking at. If you have a graph that's showing activation energy, that is when you're adding in the hill. So that energy barrier you have to overcome for the reaction to take place. So you see that hill, and when you're looking at your energy barrier or your activation energy, it's always from the reactants to the top of the hill. If you're looking at the reverse reaction, it's from the products to the top of the hill. And then the last thing is to know about catalysts, and that's if you have a catalyst, all it does is lower your activation energy so the reaction can happen faster. It is not consumed in the reaction, it just facilitates the reaction. If you are looking to look at some old diploma questions, here are a bunch of links that I will link in the comment section below or in the description section, so please feel free to look at that. If you found this helpful, please subscribe, and if there's any other type of video I can do for you, just let me know. Thank you for watching. Oopsie, there we go.